Okay, this is chapter 6 homework for our Physics 101. It says pitcher claims he can throw a .145 kilogram baseball with as much momentum as a 3-gram bullet moving at a speed of 1500 meters per second. What must be the baseball's speed if the pitcher's claim is valid? So I just want to set this so that the momentum of the baseball is equal to the momentum of the bullet. Alright, so I just say the mass of the baseball times the speed of the baseball is equal to the mass of the bullet times the speed of the bullet. And I want to know what speed must he throw it with. So the speed of the baseball is equal to the mass of the bullet times its speed divided by the mass of the baseball. I put in the appropriate numbers of 0.00300 kilograms because these two are significant. These two digits times 1500 meters per second divided by 0.145 kilograms, which is the mass of the baseball, and that gives me 31.0 meters per second. By the way, that's roughly about 80 miles an hour, so it's a decent baseball throw. Now, which has greater kinetic energy, the ball or the bullet? Now, if you get hit by a baseball and you get hit by a bullet, which is going to hurt more? It'll hurt more to get hit by the bullet. And it's because the bullet has a lot more kinetic energy. They have the same momentum, but the bullet has a lot more kinetic energy because for kinetic energy, the speed is squared. Alright, so having a bigger speed and a smaller mass gives you might give you the same momentum, but a lot more kinetic energy. So the answer for B is the bullet. Well, let's just run the numbers. The kinetic energy of the bullet is 1/2 mv squared. So that's a half of 0.003 times its speed, which is 1500. And that's equal to 3,380 joules. Now the kinetic energy of the baseball, 1/2 mv squared, which is 1/2 of 0.145 kilograms times 31.0 meters per second squared, which gives me 69.7 joules. So clearly the bullet has a lot more kinetic energy. A .5 kilogram football is thrown towards the east with a speed of 15 meters per second. A stationary receiver catches the ball and brings it to rest in 0.02 seconds. What is the impulse? Alright, well, the impulse is just a fancy way of saying it's the change in momentum. So for part A, the impulse is equal to my change in momentum. That's P final minus P initial. Alright, that's M VF minus M VI, because my masses are staying constant, as is usually the case, but not always. Can rewrite this as MVF minus VI, just factoring out that mass, and put in the numbers. I get 0.5 kilograms times VF minus VI. The final speed is 0. The initial speed was 15. And that gives me an impulse of negative 7.50, and the units are kilograms meters per second, which are just the units for momentum. Now, I also want to find out what is the force. So force is equal to that impulse over time. Alright, so that impulse is, we've already said, is minus 7.5 kilogram meter per second over time, which is 0.020 seconds, and that gives me negative 375 newtons. If I check my units, I have kilograms meters per second, and then another seconds. That makes this kilogram meters per second squared, which is a newton, and it's negative, so the ball is thrown to the east initially. Alright, its velocity is to the east, and so the force that acts upon it has to be in the negative direction in order to bring it to rest, and it's negative 375 newtons. Alright, a 730 Newton man stands in the middle of a frozen pond of radius 5 meters. He's unable to get to the other side because of a lack of friction between his shoes and the ice. To overcome this, he throws his textbook horizontally towards the north shore at a speed of 5 meters per second. How long does it take him to reach the south shore? Alright, so let's draw a little picture. It's a lake. It's 5 meters. And there's a guy right here. It says that his weight is 730 newtons. So his mass is 730 newtons over 9.8. That gives his mass in kilograms, which is 74 kilograms. So we'll just sort of tuck that away. We're going to need that. I'm going to call that mass of the guy. Now he takes a book and he throws it towards the north shore at a speed equal to 5 meters per second. And that book has a mass of 1.2 kilograms. Now by throwing the book, he's going to cause himself to go backwards, and we want to figure out what is that speed that he recoils, his recoil velocity, if you will. So we use the conservation momentum as that pi is equal to pf. The initial momentum is 0. That's because nobody's moving. The final momentum is the momentum of the book plus the momentum of the guy. mbvb, that's for the book, plus mgvg, that's for the guy. Let's just put in some numbers. Right? Mass of the book is 1.2 kilograms. Velocity of the book, or the speed rather, is 5.0 meters per second. It's in the positive direction, so it is a velocity actually. In the positive direction, north is positive, plus the mass of the guy, which we figure to be 74 kilograms, times his speed, the speed of the guy. Now notice that the speed is going to come out negative. So if I calculate my speed, it's negative 1.2 times 5 over 74. That gives me 0.081 meters per second, and it's negative, so that means that it's to the south, but we knew that already. Now we want to know how long it takes him to reach the south shore. He was right in the middle of this 5 meter pond or whatever, and so this is 2.5 meters, this distance that he's traveling. So I just say x is equal to v naught t plus 1/2 at squared. Our acceleration is 0. As soon as he lets go of the book, there's a brief time of acceleration while he's throwing the book, but then his acceleration goes away because there's no longer a force acting on him. So the acceleration is 0. I want to figure out the time, so x, or t rather, is equal to x over v naught, which is his constant speed, the vg. So that is x, which is going to be minus 2.5 meters over minus 0.081 meters per second. The negatives cancel. It gives me 31 seconds. That's the answer. Alright, a rifle with a weight of 30 newtons fires a 5-gram bullet, speed of 300 meters per second. Find the recoil speed of the rifle. So here's our rifle. Initially we assume that nobody's holding it. Maybe it's sitting on like a rail or something that it can roll backwards. And it has a weight of 30 newtons. So the mass of the rifle, let's just go ahead and figure that out. We're going to need it, is 30 newtons over 9.8. That's F over G. And that's equal to 3.1 kilograms. It says it fires a 5-gram bullet with a speed of 300 meters per second. Find the recoil speed of the rifle. So in part A, we use the conservation momentum again. Pi is equal to Pf. The initial momentum, nothing is moving. The rifle's not moving, the bullet's not moving, so the initial momentum is 0. The final momentum, the bullet's going to have positive momentum, and the rifle is going to have negative momentum because it's going in the negative direction. And so it's going to have, they'll add up to equal 0. So we have the mass of the rifle, the recoil speed of the rifle, plus the mass of the bullet, the speed of the bullet. I'll go ahead and put in some numbers here. The mass of the rifle we said is 3.1 kilograms. VR is what we want to know, plus the mass of the bullet is 5 grams. That's 5.0 times 10 to the minus 3 kilograms times the speed of the bullet, which is 300 meters per second. So if I solve for VR, it's negative 5.0 times 10 to the minus 3 times 300 over 3.1. That gives me negative 0.48 meters per second. Half a meter per second. That's not insignificant. Alright, now let's consider now that the rifle is being held by a guy. Alright, so now it's not just the rifle that's recoiling, but it's the rifle plus the guy. Now this is a bit of an estimate or an approximation, because when you shoot a rifle, the whole mass of you doesn't go backwards. But in this case, we're going to assume that your whole body, the whole mass of your body, is going to go backwards, just to make it a little simpler. But we know that really it's just a fraction of your body, more like maybe a third or a half of your body moves backwards, and the rest of you stays planted on the ground, hopefully. Alright, so have a 700 Newton man. Let's go ahead and figure out the mass of that guy. The mass of the guy is 700 newtons over 9.8. And that gives me a mass of 71 kilograms. And then I do just like I did in part A. The initial momentum is equal to the final momentum. The initial momentum is 0 because nobody's moving. The final momentum is the momentum of the guy plus, the momentum of the bullet plus the momentum of the guy and the rifle combined. So that's going to be the mass of the guy plus the mass of the rifle times their recoil speed. So this is their recoil speed. So I'm looking for V recoil, the recoil speed. I'm going to solve it over here. That's equal to the mass of the bullet, speed of the bullet, divided by the mass of the guy, plus the mass of the rifle. And this is a negative value, because we know the recoil speed, since the bullet has a positive velocity, the recoil speed is going to be negative, and that comes out in the algebra. Putting in numbers here, I have negative 5.0 times 10 to the minus 3 kilograms times the velocity of the bullet, which is 300 meters per second. That's positive. Divided by 71 plus 3.1, that's 74.1 kilograms. That's their combined masses, and I get negative 0.02 meters per second. So that's the recoil speed, which is significantly less, more than a factor of 10, than the recoil speed of just the rifle. When you add in that extra mass, really helps it. Alright, this is number 5. I notice that I've changed this problem slightly. I have a 10 kilogram bowling ball, and it's traveling in this direction. This is my bowling ball. It's traveling in this direction at 2 meters per second. It has a mass equal to 10 kilograms. And then here's my pin. Just like that. It has an initial velocity equal to 0, and it has a mass equal to 1 kilogram. All right, that's my initial state. And then my final state is the bowling ball continues going in the same direction, but at a slower speed, 0.5 meters per second. And I want to know what's the velocity of the pin. You can imagine that velocity will be in that direction, but we'll see. We say that the initial momentum equals the final momentum. There are 2 particles for each. So it's the mass of the bowling ball, which is 10 kilograms, times its initial velocity, which is 2 meters per second, plus the mass of the pin, which is 1 kilogram, times its initial velocity, which is 0 meters per second. And that's going to equal the mass of the bowling ball, is it 10 kilograms, times 0.5
plus 1 kilogram times VF. All right, so that's 20 equals 5 plus VF. So VF equals 15 meters per second. That's pretty fast. All right, but you have such a large, massive bowling ball, and it transfers all of its momentum to this much smaller object. I think that bowling pins are actually quite a bit more massive than that, so their velocities probably aren't that high. But it just gives you an idea how this very massive object can transfer its momentum to a less massive object, giving it a higher speed.